Isn't the point of inflection like when you derive it once and you derive it?
No. Okay, hello and welcome. Let's look at a few functions. Very briefly, we're going to be looking at the point of inflection. Now, the point of inflection is like a turning point. In fact, it's the turning point of the derivative function. Now, guys, if you don't fully understand that, it will become clear. And if you don't understand that, just memorize the technique to finding it. So, now let's just put this down. Point of inflection. Right? Now, as a shortcut, I'm going to put this in inverted commas just so that you know what to do with it. It is the turning point of the derivative. Turning point of f prime of x. Okay. Now, ladies and gentlemen, turning point of f prime of x. You have now already studied that there are 4 steps to finding the turning point of a function. Step number 1 is find the... So step 1 is what? Find the derivative. And then step 2 is what? Make the derivative equal to 0. And then what do? Solve for x. And then step 4 is take that x and back substitute into the original function. Okay. So I'm not going to write this down again because you guys can visit a previous video. And then, ladies and gentlemen, in this case, I'm saying it's the turning point of f prime of x. So let's do those 5 functions that we had. So the first function we had there was x cubed plus 6x squared. So this is f of x. Is what? X cubed plus 6x squared. Now we have to find the derivative. Can you help me out with the derivative, please? What's the derivative going to be? 3x squared plus 12x. Okay, so now if double prime of x is simply, let's read it like this, it's f prime of x, which I'm going to derive now, which is its derivative. What's that going to be?
It's going to be 9x. No, 6x. 6x plus 12. Yeah, plus 12.
Right. So that is step 1 of finding the turning point of a function. Find its derivative. Now we found the derivative, but remember I'm saying we are trying to find what we call now the point of inflection, which is the turning point of the derivative. So we can apply the steps to finding the turning point for this function. Okay, so that was step number 1. What is step 2, please?
Step 2.
Equate the derivative to 0, which is 0 equals 6x plus 12. Step number 3 is what, people? Solve for x. Righto. So if we solve for x here, I'm going to bring it over negative 12 equals 6x. That implies that negative 12 over 6 is equal to x, which means that x is equal to, come?
Negative 2.
Negative 2. What do I do with this negative 2?
Substitute.
Into what?
Into the function.
So I must find f of negative 2. In other words, I'm going to put the negative 2 in there. And negative 2 in there. And I'm going to get what? Negative 2 cubed is minus 8. Negative 2 squared is positive 4. So it's minus 8 plus 24. Which gives me what? Positive 16. Are we good? We state that as a point. Now remember, this was step 4. I back substitute in the original thing. And now I state the coordinates. The coordinates was negative 2 on the x and positive 16 on the y. Now I'm going to go to Desmos very quickly, and we're going to bring up this graph. And what does this graph look like? It's x cubed plus 6x squared, and we're going to see if we have the point of inflection over there. Y equals x cubed plus, was it 6? What is 6x squared or was it x squared?
6x squared.
Righto. So you know at negative 2 I must have a point of inflection. Now Desmos is very, very nice because it will give us the 5 key points here. We know that's an intercept. We know this is a turning point. We found that previously. We know that's a turning point. And then somewhere, let me just zoom in. What was it? Negative?
Negative 2 and 16.
Negative 2 and 16 is that point over there. Now what I'm noticing is it's not giving it to me. That point over there. negative 2, and 16. Do you see it? Negative 2 and 16. Now this is the point of inflection, right? Now guys, when we did this last week, Desmos was nice enough to give us, when I clicked on it, it showed up, but it's not showing up now. For some weird reason, it's forcing me to drag it. Anyway, the point of inflection is like a turning point. Now, when we talk about a turning point, you've now seen where that point of inflection lies. When we talk about a turning point, can you tell me what changes of the graph?
From negative.
The gradient.
The gradient, right? Because here the gradient was positive. In other words, it slopes upward. Here the gradient is negative, so it slopes downward. So at a turning point, make a note of that, it changes slope. At the turning point, the slope changes. Okay? But at a point of inflection, it's like a turning point, so something else changes, right? So the slope changes. Now, people, if we look at this curve that I've seen over here, right? We look at that graph. The point of inflection lies here. This is where the point of inflection lies. It's like a turning point, so something changes.
The slope.
The slope already changed. The slope was positive, now it's negative. Now it's like this.
From negative.
The bucket changes. It goes from this to that
Only one point of inflection.
on that piece. Right? And on a cubic graph, there is only one point
Is it
of
possible
inflection.
that it be more?
Not for a cubic graph. Not for a cubic graph. But you should know this. If I have a 1, 2, 3, 4, 5 turning points, this is x to the power of 6. You know what I mean? We've done this, right? So this is going to have a point of inflection there, right? There, and then another one there, another one there. Because now you're going like that, then 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 you're going like that. So 1, 2, 3, 4, 4. Are you with me? So you can bring up a relationship with that as well. And the relationship there will be, it's x, because you have 1 point of inflection for x to the power of 3. You have 4 points of inflection for x to the power of 6.
Oh.
So what's the relationship? The degree minus 2. Okay, so that's important. So I just want to bring this back now quickly. I'm just going to erase all of that. Let's get a large eraser and let's take that off. So as mentioned, the point of inflection is like a turning point. But except where a turning point changes what? It changes the slope. You go from positive to negative, right? The turning point lies there. On a point of inflection, we change something else. We change the shape of the curve from that to that, right? And this is called a change in concavity. So that is what a point of inflection does. At the point of inflection, what changes?
Cavity.
Okay, Noura. Concavity. Okay? A curve on this interval, if it looks like this, it is said to be concave down. And on this portion, it's said to be concave up. Now you should be taking notes and writing it down and engraving a neural pattern. Okay. So we're going to pause there. We're going to go back to saying, how do you find the point of inflection? So, to find the point of inflection, all we do is we say, find the second derivative. In other words, the derivative of the derivative, right? And if you go to the third derivative, it means the derivative of the derivative of the derivative. Okay. Now what you do is, you equate it to 0, you solve for x, you back substitute in the original function. Not the derivative function, in the original function, because it's a point of inflection on this first curve. Let's do the other examples now, and then we'll see what it looks like on the graph as well.